Okay, I want to give a little look at how to start working on this table, what's going on in this table, so then you can finish filling out each of these lines as we go. There's a strategy for these lines, and they're truly not random numbers, but they are due all of the different cases that we have here. All right. There's also a second MOSFET here, the BSS138. And it's a different one. This is actually the BSS138 is the recommended transistor and also the one that's commonly used on the I2C level shifter circuit. This is the model that you'll see. It's recommended in the data sheets, and it's also appropriate if you look at the threshold voltage. It's good. All right. Before we go, this is the BS170, this threshold voltage of 2.1 volts. It is for the BS170. The BS170 is the MOSFET of the day that we're using for our labs and lab work. So, of course, it's really great, is what the description says, and its features are, of course, awesome. BS170, we're using the through-hole version. It goes drain gate source when you're looking at the flat side. Remember the drain and the source. The drain and the source for these transistors, for MOSFETs, are symmetric, as we've seen how the physics works. But in this case, and in all three terminal MOSFETs, you notice how we don't have a pin brought out for the body terminal. The body is connected to the source. Okay, that connection happens inside of the black package. That's why we only have three. And because the body is connected to the source, it turns out we have a PN junction here, and we have a PN junction going this way. But if you notice, this PN junction is shorted by the connection. So this diode is really the same as this diode. But the way we draw them in these schematics is it looks like this body to drain PN junction, it looks like it's connected between source and drain. Really what's happening is the body is connected to the source with a wire, therefore it looks like it's connected. See that? All right, that's what's going on here. And there is no physical, well, there is a physical PN junction, but we don't manufacture this separately or just have like a separate diode inside this package. As you know from the physical structure, that PN junction is just inherently part of building a MOSFET. Okay, absolute maximum ratings. These are how to destroy your device. So go more than 60 volts across it between drain to source. It 5. Likely the gate to drain to gate voltage. Okay, that's gate to drain voltage. That can also be up to 60 volts. Okay, here's the one that we have to be careful with. The gate to source voltage cannot be any larger than plus or minus 20. What this means is it can't be bigger than plus 20 or more negative. The gate can't be more negative than the source by 20 volts. If the source is at 0 volts, the gate could go down to minus 20. It could go up to plus 20. This is why we can't connect the gate to the drain. It's really easy to do so. Do you see how the gate and the drain are like right next to each other? You take a little voltmeter probe or something, and you can accidentally short those together. You have 50 volts or 40 volts on your drain because your switch is off, and you accidentally connect the drain and the source together. It's really easy to do. You will blow out the gate. Blow out, basically spark across this tiny little insulator here, the O and the MOS MOSFET, and punch a hole in it and destroy the device, and it won't work properly. It'll do something, because physics is always going to do something, but it won't work like a transistor. This is an enhancement mode transistor, which really means that the threshold voltage for the N channel is positive. All right, if we flip the page, we can see that. My pen around. Okay, on characteristics, gate threshold voltage. It's between 0.8 and 3 volts, and it's typically 2.1. This range should terrify you, all right? If you're going to use a BS170, you need to ensure that your circuit will work fine. If you are extremely unlucky and your particular MOSFET has a gate threshold voltage of 3 volts, okay? Unlikely, but if you want every single one of these products rolling off of the production line to just be guaranteed to work according to the datasheet, then ensure it works with 3. I'm going to use 2.1 for this, and it can be lower. All right, that's a huge range. All right, this is not like a 0.6 volts for a PN junction because the gate threshold voltage is not a PN junction. All right, we also have a on resistance of 1.2 ohms, but notice that you're only guaranteed 5, much bigger than 1.2. Okay, other capacitances. Such. I really like data sheets. You should too. Drain to source current. So if your gate to source voltage is 9876543, and if it's lower than 3, I think 3 is a common number. Have you seen 3? Right there, gate threshold voltage. Right? If it's lower than 3, the thing is off. There's no current, no matter the voltage. If we turn this on to 5 volts, which is what we're going to use for our circuits, we have a inflection point at about here-ish. And that's where the drain to source voltage, where there's a channel on the source side, and then the channel on the drain side goes to 0 thickness. Okay, we talked about that in class recently. And so on, as we get more gate to source voltage, we get more current because the channel is thicker. There's more charges in the channel to move, and that gives us more current. The other dimension is DS. As the drain to source voltage gets bigger, voltage across the channel, sideways I guess, we do get more current as well, until we hit saturation mode. And at saturation mode, we can't get any more current, right? So it stays flat. So at this inflection point here, this really is a parabola going up, or at least the theory shows a parabola here. So here is triode mode, and in this region is saturation on this plot, right? The slope of this line is 1 over resistance, because this is amps per volt. That slope right there is 1 R. And we go to the next figure, you see on resistance with gate voltage and drain current. So if the gate voltage, gate to source voltage is 4, we get so much drain current and we get resistance, right? If the gate voltage gets larger, we go here, it's 5, it's 6, it's 7, it's 8, it's 9. You see how the resistance decreases, right? So 4 volts, 4.5, 5, 6, 7, 8, and it goes. Does this look like 1 ohm? It looks like 1 ohm, but actually this is, this y-axis is RDS on divided by R, nominal or something. So whatever this R nominal is, maybe that's 1.2 ohms. Maybe it's a different resistance, but this is not units of ohms. It's normalized. So when we get up to a 2, this means the drain to source resistance is double. Here it's triple whatever the numerator, the denominator is. So be careful with that. 1.2 is, I'm getting that from right here. Drain to source on 1.2. Remember, you could, if you're really unlucky today, have a 5 ohm on resistance. I've never actually seen that in lots of years of dealing with the 170. So, use the guaranteed one if you want to be guaranteed to work. Oh, by the way, the on resistance changes when temperature. Of course it does. And the on resistance changes with temperature. Drain current. There are many variables going on, so we can plot these. Another plot that I just want to take the opportunity to point out is this one. This is drain current versus gate to source voltage. All right, so let's say I apply 5 volts across this device. Let's do 6. All right, so I'm going to look at 6 volts as the gate to source that's already labeled on here. At normal temperature at 25 C, the drain current is so many amps. Okay, and that's with a VDS of 10 volts across it. We're only using 5 volts, so we'll get much less current. Be about half. Well, if the temperature gets bigger, the drain current goes down. You see how we go from 25C to 125C for the same gate to source voltage and the same drain to source voltage. Nothing in our circuit changed, just the temperature of the transistor. The drain current is going to go down. So you might think of this like RDS on as a function of temperature. It has a, what happens to the resistance? So if the temperature goes up, the current goes down for the same voltage. That would be, let's see, temperature goes up, current goes down, voltage is the same. We have V same over I decreasing. That means resistance goes up, right? So this would be plus something ohms per degree Celsius. Call this a positive temperature coefficient. If you want to sound fancy, you call it a tempco. Oh look, but here's another thing. The gate to source threshold voltage has a negative temperature coefficient. Interesting. These two kind of trade off against each other, and be careful. You can end up with a condition in a MOSFET circuit called thermal runaway, where the current increases, which increases your power dissipation, which increases the temperature, which increases the current, which increases the power dissipation, and things just blow up. A few minutes of operation. All right, so I don't feel too bad taking some time to deal with that. Look at this. All right, VG, the gate voltage of this MOSFET is 5. The source voltage is 0. The drain voltage is 0. So this would be VGS is 5. VGD is 5. See that? So gate to source is just G minus S. That's 5.0 volts. VOV, remember, is VOV is VGS minus V threshold. VOV needs to be a positive number for us to have a channel on the source side where I'm pointing. And VOV is, the larger that VOV is, bigger than 0, the thicker of a channel. It's always, we see VGS minus the threshold. Sometimes we replace the subtraction with VOV. Sometimes you also say V effective. Depends on who's writing the book. All right, so this would be 5 minus 2.1, 5, 4, 3. 2.9. Okay. What is VDS? Well, it's drain minus source. It's 0. Okay, what mode is this in? So gate to source, is that above the threshold? Yes. VOV is positive. Now we need, is there a channel on the drain side? So that would actually be gate drain. We don't have, DS is the other term that we use in circuits. Okay, but if you're going to follow the channel, it's gate to drain. Gate to drain is 5 minus 0. It's 5, so it's yes, yes, which is a triode. All right. I would ask if there's any questions, but there's no feedback in the video. Let's go down to row 1, 2, 3. Unless you're a computer engineer, this is row 2. All right. What's VGS? It's 5.0. What is VOV? It's the same. It's 2.9. And what is VDS? It is 4 in this case, 4.0. Is there a channel on the source side? Source side, that would be gate to source, 5 volts. 5 volts above the threshold. Yes. Yes. And is there a channel on the drain side? So we go gate to drain. 5 minus 4 is 1. Is 1 greater than 2.1? No. If we get a yes and a no, this is saturation. Okay. Anything else? Make sense? How about this one? This is the same, so there's a channel on the source side. This one is 5 minus 8, which is a negative number. Is a negative number bigger than 2.1? No. We're going to end up in saturation mode. I'll let you fill out the rest. All right, hopefully that should be clear on how to fill out this table. These numbers, just be careful, do each one individually and consider these things. Voltages, just go slowly and it will actually take a short amount of time. Be careful with negative numbers. Subtract negative numbers properly. All my only advice. Here we have a similar situation, but our threshold voltage is different. You notice this is 3.3 and 5 volts and 0 volts. These are the voltages used in the I2C level shifter. Watch those, what we do. All right, so this is just some notes on the situations, the source and the drain. The source is at 3, the drain is at 0. This is also going to forward bias the drain body junction that you see in the video, other I2C video. It will be a temporary condition, so just any forward bias PN junctions in this one, you need to draw the structure sideways view of an N-type MOSFET to see where the PN junctions are, to get the voltages on the P side and the voltages on the N side, and then you can answer that question. That's it. Thanks.